All right, so today we're going to continue. In fact, we're actually going to conclude with arrays. We just have a few minor things to conclude with, and then we'll do some exercises. And then on Wednesday, our last day before spring break, I'll go ahead and run you through some basic usage of some tools like Valgrind, GDB, and stuff like that, because when you come back from your break, you'll be doing a hack based on GDB. Remember that we left off with talking about arrays with, creating dynamic memory, passing them to functions, passing them back from functions, things like that. What I want to do now is I want to show you the consequences of something called a shallow array versus a deep array, or a deep copy. It's shallow copies versus deep copies. So to do this, what I'm going to do is I'm going to set us up as a review. Remind me, how can we create a small array to, say, hold 10, 20, and 30? Now we could do this with a static array, but remember static arrays are on the stack, right? And they're, you're abusing the stack space. As long as they're small and unchanging or whatever, that's fine. But let's go ahead and make a dynamic array here. Dynamic arrays are done using pointers, right? And I'll go ahead and call my array A for now, okay? You typecast whatever malloc gives back to you. And then what do you pass into malloc to get an array of 3 integer arrays here?
Malloc, whatever, however much space that you want.
How many bytes you want, exactly. So how many bytes do you want for 3 integers?
Size of int.
There you go. So you could go ahead and hard code this at 12, but that's not great practice, right? Instead, you want to size of an integer. That gives you the number of bytes in one integer. And if you want 3 of them, then multiply that by 3. And in this case, I'm going to go ahead and put that into a variable so that I don't have to hard code that value over and over and over again, okay? All right, now let's go ahead and put values into that array. A sub 0, I'll set that equal to 10. A sub 1 is equal to 20, and A sub 2 is equal to 30, okay? Now if I were to print these out, it of course would be 10, 20, and 30, right? And we won't visualize this execution since it's so easy, simple. But what I am going to do is I'm going to create another array over here, int b, right? And I'm going to set it equal to a, right? This is what's called a shallow copy, right? And then what I'm going to do, yeah, go ahead.
So, just looking at how you create int a, I don't fully remember what does the int star mean, in the declaration. I know malloc size of int is how much space on how much space that you want, or how much space you want. So what is the int star
on this one?
Yeah.
That's the typecast. There's only one malloc. Malloc just gives you back a void star pointer, right? A generic void pointer. If malloc just says, here's this chunk of memory, use it however you want. If you want an integer array, then you're going to treat it as an integer array. If you want a double array, you're going to treat it as a double array. And when I say treat it as, I mean typecast it to the appropriate type.
So that is just the type.
It should match this over here.
Okay,
right?
so it's just whatever you're storing, or the type of whatever you're storing.
Right. If I did something like double and double, right?
Then you'd be storing doubles.
I'd be storing doubles, but would I have enough space for, say, 3 doubles now?
No.
Nope.
You would have to change to.
I would have to change this to a double as well. In fact, double is going to take twice as much space. So I've only asked for, say, 12 bytes here when I actually need 24, right? And that means that I'm going to be accessing memory that was not allocated to me. Okay. Undefined behavior.
Okay.
Right? Undo, undo. There we go. So this is called a shallow copy. Why? A and B are pointers. They point to things. What is A pointing to right now? That array that we just created. What is B pointing to after line 11? A, the same thing, right? We've got 2 pointers pointing to the same thing here. Right? So if I change, say, B sub 0 is equal to 42, what value is now stored in A sub 0? If I were to print it out, percent A sub 0 is equal to percent D and the line, A sub 0. Remember, we originally set it to 10. Did we directly change the contents of the array A? Not directly, but what ends up getting printed here? Let's visualize this execution. Again, remember, these are 2 pointers. They are pointing to the same thing. Right? There we go. Let me go ahead and walk through this. Right? So we've set up the integer array here. A is now pointing to an array of size 3. Okay? We fill it up with 10, 20, and 30. Right? Now we make pointer B point to the same thing. Right? See, they're pointing to the same, there's only one array here. It's pointing to the same thing. And so when I go and change B sub 0, what is B referring to? It's referring to that 10 right there. 10 gets overwritten. So if I print out what's in A, well, what's in A now? 42. That's because I've got two things referencing the same memory location. Okay? That's known as a shallow copy. That's not really what we mean by a copy, though, right? If you said, give me a copy of an array, right? And then, okay, here you go, here's your array, and somebody else had the original reference to the same array, and they go and change that array, right? They've changed your data. Right? So does that sound like what we mean when we mean I want a copy of something? Probably not. So this is a shallow copy. What do you think is the opposite of shallow? Deep, right? So let's make a deep copy. How can we make a deep copy? We'll take and create a brand new array. Instead of making these two things point to the same thing, I'm going to make B point to a brand new array, and then I'll copy over each element. I'll copy 10, 20, 30, 40, whatever is in there. And then I will go ahead and make changes to B, which will not be realized in A. All right? So I'll go ahead and remove this. There we go. And bring this down here. So how do I do a deep copy? Well, int star B is equal to int star malloc, right? Size of int times n, same exact size, right? And then I will copy over each element. For int I equals 0, I is less than n, I plus plus, an idiomatic for loop for iterating over elements in an array. And I will copy into B sub I the contents of A sub I. And remember, we are online, so if you have any questions, go ahead and post to Piazza or to the YouTube live stream here. Right? Now, when I make changes to B, does that affect A? Let's find out now. Right? So let's visualize this execution here. And again, a deep copy is just a completely new memory location. So when I run through this example here, and I'll run through the initial code pretty quick here, 10, 20, 30, there's A. I create a brand new copy, brand new allocation of memory somewhere else, and copy over the elements 10, 20, and 30. Now you see that these two pointers are pointing to completely different things. Changes to one will not affect the other. Right? And so when I make changes to B, now B is affected, but A sub 0, 10, is unaffected. So when I go to print it out, I still have the original value 10. That's a deep copy. So let's get some more practice here by generalizing that. Let's go ahead and put this into a function. Right? What I mean by that is, let's go ahead and say creates a deep copy of the given integer array of the given size, right? And returns a new deep new array. I'll go ahead and leave it like that. Yeah.
Is there a reason you would want a shallow copy?
If you, technically speaking, anytime you pass by reference, you're shallow copy, right? So I do want to make changes to it over there, right? If you're passing it and shallow copy but with a const means it's read-only. So here's a shallow copy, like if it's a million integers or something, that means I don't have to copy over 4 megabytes just to give you a copy that you're not going to change anyway. So here's the shallow copy, a reference to the original, put a const in front of it, you can't change it, right? So if you have no call to duplicate the memory, basically, then you want a shallow copy because it's way more efficient. Right? All right? Help me write this function. I don't know, is this big enough for those in the back? Okay. So help me write this function. What should I call it, first of all?
Copy.
Okay.
Deep copy.
Deep copy, all right, I like that even better. In fact, I'll also slap an int on it because I'm only gonna make it apply to one thing, okay? All right, this is just the prototype. So tell me, what's the return type here? Is it just gonna return one integer?
It's gonna return an
An array of integers, and we represent that with a
star.
pointer, int star. And I will take an integer array, int star, original, if you want to call it original. And anything else?
Do you take
Somewhere to put the new array?
Somewhere, well, I'm returning it. So we'll take care of that when we actually write the
Okay.
function. What else do I need to know?
the number of things going in the array?
The number of things in the array, right? So int n, always the size. Yeah,
Do you have to stay int star equals or not?
where?
Like, in 22 in the prototype, you have to say int star equals.
Nope, that would not be the type, right? Would you say, if we wanted to return one integer, would you use that syntax? No, right?
Okay.
It's like this. Int star is the return type.
Okay.
But and in fact, you can eliminate all white space here entirely. It doesn't look great. But usually the style is to put a space between the int and the pointer, and then no space with over here. Don't ask me why. Some people like it like this.
That's how that.
Some people like it like this. Some people do not listen to them ever like it like this. Right? Never do that. Right? Yeah. It's not reification. It's from the perspective of C. This is syntactic sugar that allows you, because of the way that arrays work, right? The indexing is a memory offset, and so if it's, as long as it is a one-dimensional simple array, then this is equivalent, all right? But then you forget that it's a pointer, right? And you forget, oh, I don't have to manage my memory. I don't have to think about all this stuff. So no, this is the preferred, right? And again, you might have seen this too, right? White space generally doesn't matter there though. Okay. All right, so let's write this function now. What would it look like?
Is it just what we did before with the for loop?
Exactly. All of this stuff here. In fact, I'm just going to edit this and grab this, bring it over here. And instead of calling it B, I'm going to go ahead and call it copy or C or whatever. And instead of copying from A, I'm going to go ahead and go original. And because I already encoded N, the size of it here, we're good. Am I done? Let's find out. GCC, all your warnings, demo.c. What's one warning?
Forgot to return.
I forgot to return. What should I be returning in this case? Return the copy. All right. There we go. So, do the same thing, but for doubles. All right. What would change?
Would it be size of, and then
Size of changes.
would it be wherever there's just an int, you put a double?
There you go. All right, let's do it for chars.
Same thing, just chars wherever there's a double.
Exactly, char, char, char. Does this seem like a good pattern to follow? Oops, no, that one, that one, that one, and that one. Does this seem like a good pattern to follow? Copy, paste, copy, paste, copy, paste, change the type? No. This is why, hopefully I'm driving home the point here of why we have malloc the way that it is. There's not a malloc for integers, there's not a malloc for doubles, there is a malloc, period, right? In fact, if you want to do something like this, do a deep copy, there's yet another function called, hopefully there's man pages here, MemCPy. Oh, fine, MemCPy. There we go. So, what do you think MEMCPY stands for? Memory copy. Right? What does it operate on? Not integers, not doubles, not chars, or on void pointers, right? In fact, it takes a source, which is constant, meaning that it is making the promise, right, that it will not make changes to your original array. How many bytes do you want to copy from the source into the destination? The only difference here is that it is going to assume that the memory has already been set up in the destination. So what I mean by that is we could go ahead and rewrite this function and use MemCopy, but the only difference would be that for loop. All it would be was memcpy into copy the original, and how big it, do you want it? Well, it's going to be exactly the same size as this right here. Right? So using memcpy will only save us on that for loop. Right? It's still generic. It still operates on void pointers. Why? Because you don't want to have a deep copy integer, a deep copy double, a deep copy char. Right? It is as generic as possible. Right? All right. And then we can, of course, change this to be const. Why? What's the difference now? What's the difference between that and this?
You're promising not to touch it.
I'm promising not to touch it, and, well, I will touch it, but I won't change it, right? I'm going to look at it and take out its values and copy them over somewhere, but I'm not going to change them, right? Excellent. Okay. I'll make sure that you have this in your notes. Any questions online? Will you teach DSA? I assume that you mean data structures and algorithms, and if you're talking about this summer, this is an online question, then no, I will not be. Right? Okay. All right. So that's one-dimensional arrays. Let's talk about multi-dimensional arrays. Right? What are those called? When I say more than one dimension, right? The regular old arrays are 1D arrays, one dimension, right? X, 1D arrays. 2D arrays are, so if you've got one dimension, you've got then two dimensions, X and Y. What do we call those things? No? Tables, right? Or, think math. Rows and columns, and in linear algebra that is called matrices. There we go, matrices, right, etc. Right? You have rows and columns. Okay. You can therefore have 3D arrays, 3D, 4D, etc. Rethink what you are doing. There is cause to have 2D arrays. In fact, in your hack on this Friday, you will be working with two-dimensional arrays representing an image. Why? An image has rows of pixels and columns of pixels. And you will take what you've been working on over the last 2 weeks, sepia, and you'll actually be, or I think you already, we gave you an image driver already, but you'll be modifying images in other ways. You'll take this image, which is a matrix of pixels, and then you'll flip it so that you can get the reverse image. Or you'll flip it upside down. Or you will, what's another one? Or rotate it, right? So that if you have a 100 by 200 image, you can now have a 200 by 100 image, and then you can flip it, rotate it 90 degrees, whatever, right? Those are the things that you'll be working on in your hack this week, right? So, if regular old arrays are int stars, we'll just consider integers for now. 2D arrays would be, what do you think? Star, star. All right, exactly. One dimension, two dimension. So 3 dimensions would be int star, star, star. I think I said 3 times. Right. 4 dimensions would be 4 stars, 5 stars, 6 stars, etc. That's why you don't want to get into it, right? If you've got the 2D arrays make perfect sense because you have matrices in linear algebra. You have tables of data. You have grids of pixels, right? Or grids in a game or something like that. Here, 3D, there's probably a better way of doing it, right? You really have no cause to go 4D or above. So rethink what you're doing, okay? So what we're going to do is we're going to create a dynamic 2D array, right? What we'll do, right? We'll create a dynamic 2D array, and then we'll modify its contents using 2 indices, right? So for example, if I have and I'll call it matrix, right? Because that's what it is, or table, or whatever you want. You're going to index 2 things. You're going to index the row, and then the column. Right? And you provide, I want the ith row, the jth column, or in this case, the row-rowth, and the col column, right? And that gives you one individual element in that table. Right? I'm going to start over here with this C visualization because I want to show you what it looks like when you've got that two-dimensional kind of thing. Right? So let's go ahead and create, say, number of rows. Well, how many rows do we want? Keep it small.
3,
2? Oh, 3? Okay. And how many columns?
2,
Let's go a little bit higher.
4.
Maybe 4? Okay. All right. Rows and cols. All right. Now, if this were a regular old array, what would I do? Int star array is equal to int star a call to malloc, int size of int times and rows. Right? And usually sometimes we use n and m instead. The number of rows, number of columns. I'm being more explicit here. Number of rows. In fact, let's go with num rows and num columns. Right, there we go. Right, and so num rows. That would only give me a one-dimensional array. How am I going to get two-dimensional arrays? Well, think about one row. Right? One row is going to be a regular old 1D array. The second row will be a regular old 1D array. The third row will be a regular old 1D array. So I'm going to do something like this, but for each row. Right? So let's go ahead and build on that. For int I equals 0, I is less than num rows, I plus plus. Right? We'll get rid of this. Right? What I want to do is I want to create the ith row. So create the ith row. So something is going to have to make a call to malloc of an int star, and this is just the regular old array here. Malloc, size of int, times. Now, think about how big that one row is. How many values do I want in that one? Just one row. Say the first row.
However many columns.
However many columns there are. So, num columns. Right? Now, where am I? Keep saving this. Where am I going to store this thing? Yeah.
So I have a slightly different question I wanted to ask. So in this 2D array arrangement we're making, every row would have 4 elements. But in something like, for example, like an array of strings, like the like RB, wouldn't those rows?
Ah, you're looking ahead because you saw the char star star, right? Oh, well, that must be a 2D array.
Right, but not all the rows are the same length.
Nope, not necessarily. They're going to compactify everything so that it's all one. If you're interested in how that works, watch video 7.5. At the end, I show you how to do what I'm doing here in the spirit of how they did it there.
Okay.
Right? If we have time, we can look at it too. Right? All right, but what I want is, this is just one row. So what I need is a way to index each row. So I'm going to go ahead and create a matrix out here. Int star star, a two-dimensional matrix. Matrix, right, is equal to a call to malloc. Okay. Now this is going to be 2 dimensions. So what do I do over here to typecast what I get back? Also 2 dimensions. Right. Now I want size of something times num rows. Right. I want. What do we say, 3? I want 3 rows. The first row, the second row, the third row. Think about just one row here. What is it that is referring to that row? What am I doing here? A pointer, right? So, what do you want? You want a pointer, right? This first pointer will point to the first row, which is created down here. The second pointer will point to the next row. The third pointer will point to the third row, et cetera, et cetera. Right? I want an array of pointers. I don't want an array of integers, because that would be a regular old 1D array. I want an array of pointers, so that each one, don't think of it like this anymore. Think of it like this, and then they're all pointing like this. Right? Question?
So you have an array of rows, and then that array is actually full of pointers that points to a bunch of different arrays that actually stretch across the image.
Exactly.
Okay.
Now, let's go ahead and visualize this. All right. There's matrix 3 and 4. So it'll be a 3 by 4, right, matrix. And the way that we do that is we set up this array right here, an array of 3 pointers, 1 for each row. Row 1, row 2, row 3. On the first iteration of this, we set up the first row. So we're going to make this first pointer point to a row of size 4, the number of columns that we have. The second iteration will do it for the second row. The third iteration will do it for the third row. Now look at this thing right here. What is this? It is a 3 by 4 table, a 3 by 4 matrix, a 3 by 4 two-dimensional matrix here. Once I've got that, and let's go ahead and edit this code now, I can treat it like a regular old two-dimensional matrix. And the way that I do that is matrix of 0, 0, right? You need 2 rows, 2 indices now, is equal to 42. Matrix of, so that's the top left one. What is the bottom right one? What would the last row be?
3, 4.
The last row would be,
4.
so the rows run from
Oh, 0 to 2.
0, 1, 2, right? So 2 is the last row. And then the columns run 0, 1, 2, 3. 3. Let's visualize that execution. And here I'm going to go ahead and speed it up since we already went through it once. There we go. Run through, speed run, there we go. And matrix of 0, 0 is going to end up being this one. Why? 0, and then that jumps to this array right here, and then 0 within that array. And 42 is set. The bottom right is going to be 2, the last pointer here, jumps down to this array, this row, and then goes to the 4th element at index 3. So this will be the last one over there.
So it's just like for each row, or for each column of the array, there's a pointer that points to a row of however many numbers you want in.
Exactly, yep. And it's a nice, not square matrix, but it's a nice full rectangular matrix. Sometimes rectangles are squares.
And then you just set that up in like a loop then, like the
Yep.
pointers and everything, okay.
Here, yeah.
So is it generally best to point to columns or rows, or does it matter?
This is the default. If you were to take a linear algebra course, of course it would be in a row major form, right? Where if you've got 2 coordinates x and y, or I and j, then it's always going to be row column. That's row major form. If you swap that around, it'd be called column major form, and then you'd be like weird, I guess. I don't know. Maybe some linear algebraists would do something like that. I don't know for what reason, but usually it is. I mean, it's just a chunk of memory. It's not actually physically like
Or,
this,
no,
right?
But is it, I was just asking, I guess if that was convention, like you have an array that would technically be your quote unquote row, and then you point to the vertical column.
Exactly, yeah.
That's convention.
I mean, this is one way of doing it. There are at least 2 other ways of doing it. The one that he was alluding to over there. I don't necessarily want to show it because I don't want to give you 5 ways of doing the same thing. I want to keep it simple. If you're interested, read the book and watch the video 7.6 or whatever it is. Right? And then later on when we do structures, we'll come up with it again. Basically, it's the way that you can do this is instead of having that row over there and that row over there and that row over there, what you can do is you can do one contiguous chunk of memory, and then through pointer arithmetic, make it point to the first element, then 10 elements over here point to the second. So you basically you make it look like it's 2D, even though it's just one really, really long array, right? Where here's the first row, and then right immediately after that is the second row, right immediately after that is the third row. And then there's yet another convention where you don't have 2D arrays at all. You just do the math yourself. For example, if you wanted the next row, what would you do? If you want the ith row times num rows, is this it? So 0, I could do something like this, plus j, right? So I want 0, 0, this will work out exactly the same. If I want 1, 1, right? Then 1 times the number of rows is going to be 3, plus 1 is 4. It'll end up being the 5th element, right? So I don't want you to have to do that math, though. Yeah.
So when you have the matrix and the 2 sets of square braces after it, what exactly is that syntax doing or
All right.
implying?
So we'll break it up here. That is a memory location, right? So what I'm going to do now is I'm going to bring in the first index. That's a memory offset location. So if it was pointing to this memory address, XYZ, now it's 0 off of that, which is still XYZ. Right? Okay. Now jump to that memory location and go 0 bytes away, right? And so that's why, it went from matrix, let's see. Let's visualize this, and then I'll jump, basically. It's jumping around in memory locations. It starts out at, there we go, next. There we go. All right. When you go to 0, 0, it starts here. Right? 0 memory offset, so now we're here. 0 memory offset, so it jumps down here. It's a dereferencing operator. Right? If you have a pointer, int star, and you put a, and then you put a pointer, a star in front of a, what are you doing? You're jumping to that memory location to treat it as a regular old variable. Here, there are 2 jumps.
Okay.
Right?
So, okay. That makes sense.
1 jump, 2 jump, regular old variable, 42.
So arrays were just a lie the whole time?
Yeah, arrays are just memory. Yep. Okay. Let's go ahead and, I don't know, write a loop now. If I wanted to set all of the elements, for, say, to 10, 20, 30, 40, 50, all the way up to, how many do we have total? 12. So the last one would be 120. What would it look like? I'll start at value is equal to 10 here. If I'm going to iterate over a matrix, what do I need to do? 2 for loops. Right? For each row, dot, 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 and I'm going to have int I equals 0. I is less than num rows, I plus plus, and this one will be for each column, dot, dot, dot. Can I use I again?
No.
Nope, j, and j is less than num calls, j plus plus. Okay. And if I want to set it to that value, matrix sub I j is equal to value. There we go. And then I'll increment the value by 10. So I'll have 10, 20, 30, 40, 50, 60, 70, 80, 90, 100, 110, 120, right? Don't make me count too much. Oops, what did I screw up? Oh, there we go, comma instead of a semicolon. Thank you. Yeah, close that. All right. So again, running through the memory setup here. Once we got that, you can either set individual elements and then printing them out would be the same as well. Or you can say, go through into a big for loop here. For the first one, 0, 0, 10, then 20, 30, 40, then the next row, 50, 60, 70, 80, right? And then the outer for loop goes to the next row, right? 90, 100, 110, 120. Look familiar?
Was it the multiplication table? Was it the same, like?
It was basically the multiplication table, exactly.
Was it the same, like procedure kind of that was?
It's very, very similar, exactly. In fact, you'll be redoing that and creating a matrix full of those values instead of just printing them out in your lab this Friday. All right. So after we're done playing with our toys, what do we do with them? Put them away. So I can free the matrix. This is my first attempt, and it's going to be wrong, right? There we go. I'm just going to fast forward here all the way over here. Next. There we go. All right. Oops. All right. There. Now, before I execute this line here, where I free up the matrix, what is matrix, the pointer, referring to? It's only referring to this array right here, right? The array of pointers. If I end up deleting this, what happens to all of these guys down here?
They live on forever.
They live on forever as a memory leak. Right? Ooh, cool. There's even a poop emoji telling you that something happened, right? Right, so, memory leak. Edit this code again. What do we need to do in order to free up the entire matrix? I need to free up the first row, then the second row, then the third row. Once I'm done freeing up each row, then I can free up the array of pointers. So it's going to look exactly like this, but in reverse. For num rows, free this matrix, or here, free the ith row, and then we can free this matrix. Let's visualize that. Has anybody taken, timed it? Are they right? Could take up to 10 seconds. There we go. Come on, there we go. All right. Now, fortunately, I don't have enough reason. There we go, I'll zoom out. All right. So what I'm going to do is I'm going to free up the first row. And now it's gone. Right? You can even see that it went to a poop emoji here, right? That it's gone. But it's not leaked, right? It is actually gone. And then the second iteration of this frees up the second pointer. The third iteration frees up the third row. And now I am free to free up that matrix. Great, no memory leaks. Okay? So edit this code, and I will make sure that you have a copy over here. Questions on two-dimensional arrays? Again, you can have three-dimensional arrays, four-dimensional arrays, five-dimensional arrays. If you find yourself doing 3 or above, really rethink what you're doing.
So would like the three-dimensional array or above, would they use kind of the same logic, just with more?
More loops, more pointers, more stars, and then 3 indices, I, J, K instead.
What would be like a reason to use more than 3? Is there any like?
I mean, if you wanted to do like grid in 3 space, maybe, like Minecraft or something like that. I don't know. Then you have a coordinate system for a 200. Is it 256 by 256 by 256?
I think so.
What is vanilla Minecraft? What is the limit?
Oh, it's like whatever.
They changed it.
They
Like,
changed.
it's 32 million in the positive and negative direction.
Oh, okay.
Some odd.
32 million, really?
Whatever the integer nearest power of 2 is.
Okay. All right, I was thinking 256 by 256 by 256. No, okay, never mind. Yeah, but if you wanted to keep track of all that stuff, then you could load it all into one big memory. You wouldn't be able to load that stuff all into one matrix. You're gonna. That's why you can't see stuff far away, I imagine, right? Yeah. Once you get closer, then it loads it up. So it only keeps chunks loaded in memory of where you are in the immediate space. Right? But if you had a much smaller Minecraft world, then sure, you could keep track of all three-dimensional coordinate systems with a three-dimensional array. Instead of integers, though, it would be blocks or rocks or whatever it is. Right?
Keeping track of your 40 chess moves or something.
So you could do, yeah. There you'd only need 2 dimensions, though, right? That's a little bit different because you'd probably do backtracking, so you would go down some computational path, and then you would just come back up, and then go down a different path. Right? You wouldn't want to keep them all in memory at the same time because that's astronomical. You'd run out of memory really quick. Right? That's going to grow exponentially. Right? Yeah. Nope. You can't even keep track of all possible card deals in a 52 card deck, right? That's already more than the number of atoms in the universe. So, but nobody has I can guarantee you, nobody will ever have a computer that big, right? With that memory that big. All right. So let's go ahead and conclude here. with another exercise that brings together basically everything that we've done so far. What I want to do is, given the integer array of n elements, this function filters out all even numbers, right? Returning a new copy, a new array containing only the odd numbers, right? And I'm going to call this filter evens because you're filtering out the evens, right? What would this look like? What's the return type going to be here?
Be int, right?
Int, just one?
It'd be int
Star? Okay. Let's look at an example here. So if I gave you the array 0, 1, 2, 5, 7, 3, 2, 8, 9, right? If the input were here, this, example, input, example, output. Align it. So would we include 0?
Wouldn't
No.
it be 5, 7,
5,
9?
7, 3, and 9. We filtered out the evens. And by the way, 0 is even, right? It is divisible by 2, right? Okay. So what's the return type? It's going to be a brand new array, right? A brand new integer array here. What are we going to take as input?
An array of numbers.
An array of integers. Good. Anything else?
Would you need the size of that array or no?
Always with bookkeeping. There's no way that you can tell, given a dynamically allocated array, there is zero way. There's not even a way that you can do syscalls in a portable manner to get how much memory was actually allocated, right? You'd have to basically do operating system level stuff, and then you would be like extending the standards instead of actually adhering to the standards, right? Before we actually implement this, though, am I going to be making changes to your original array?
Yes,
Oh.
because you're taking out the,
Well, I'm just going to look at your array, and I'm going to produce a brand new array.
so that no, you're not making
Well, you
changes.
shouldn't be, I guess.
Okay, I shouldn't be, right? So let's make that promise, right? Const. And again, it's kind of a pinky swear, right? You can break that promise. There are circuitous ways of breaking that promise that I won't get into, but we'll be good actors here and not break that promise, right? All right, obviously I'm going to want to return a new array. So int star result, say, is int star call to malloc size of int times, wait a second, how big is the resulting array?
However many even numbers.
However many odd numbers are in there, right?
Yeah.
Okay, do I know that?
Not yet.
Not yet. Good. Excellent answer. So what should I do? Go through it and count. And well, not take out yet. Count the number of
Oh, before you make the array, you have to count. And
Right.
Then you make the array, and then you pull the numbers.
int num filter even, so num odds is what I want, right? And I'll start this at 0 because if I don't start it at 0, what value is in that variable right now?
Just whatever.
Who knows? Dead beef, right? For int I equals 0, I is less than n, I plus plus. We will count up the number of odds. If array sub I, how do I tell if something is odd or not?
If you divide it by 2 and the remainder is 0.
If I divide by 2 and the remainder is 0, excellent. Then I go num odds plus equals, or is equal to num odds plus 1. Shorter way of writing that is plus equals 1, even shorter, plus plus. Excellent. Okay. Now I know how many odds are in there. Num odds. And ultimately I'm going to return this, return result. Okay. Does it have the values in there yet? Does it have all the that 2, 5, 7, whatever else is in there?
No.
Nope, not
Just
yet.
knows how many there are.
Just knows how many there are, and it's allocated the memory. Has it copied them over yet? No. So let's do that. Again, another idiomatic for loop here. For each element in ARR dot dot dot. Again, if it is odd, I want to add it. If it is odd, add it to the result dot dot dot. And by the way, this I'm just doing these for presentation purposes. You would never actually leave this kind of document. It's perfectly fine to write that kind of documentation to keep it all straight in your head, right? But that's crufty documentation. Don't leave that in your final submission, right? The code is self-explanatory. Once you've written this and you read the code, you know what you're doing. You're iterating over the elements, right? You know that you're checking to see if it's odd. Right? The code tells you that. You don't need another duplicated English sentence telling you what it is, okay? All right, so if it's odd, where do I copy it to?
The new array that we,
The new array results of I is equal to array sub I? Okay. Let's see this in action. I'm going to go ahead and copy over this entire thing, get rid of all this stuff.
you don't have to like free that up at the end, do you? Or is
All right, hold on to that thought, and we'll come back to that.
Okay.
On who who owns this memory now, right? So let's go ahead and create an array here. In fact, I'm just going to go ahead and take the example array that we had up here. Right? Here's the original. Get rid of this. Right? Int, and I'll just hard code this as a static array because I don't want to set it up. And then int filtered is equal to a call to filter evens of array. There we go. And how many things are in this? 8. And there are 8 things in there. Okay. Let's visualize this execution. Hopefully it's syntactically correct. I think it would have come back sooner if it weren't. Excellent. All right, let's walk through this. There's the original array, 0, 2, 5, 7, 3, 2, 8, 9. All right, and now we're going into our function here. We're going to go through and count up the number of odds, right? So that's not odd. That's not odd. We've now found 3 odds, right? 5, 4, and then we're done. We found 4 odds, right? 2, 5, 3, and 9, right? So we've got 4 of them. I set up a new memory location exactly of 4, right? Now let's walk through this. Is 0 odd? Nope. So that doesn't end up copying it over. Okay. Is, well, where are we now? 1 is 2 odd? Nope. So we don't end up copying it over. Is 5 odd?
Yes.
So we end up copying it over. Did we copy it in the correct location?
No.
Nope. I is an index variable for which one of these arrays?
The first one.
The first one. Can we use it for the second one, which is of a completely different size? Nope. Back to the drawing board. So I need another index variable. J, all right. And I'll copy over J.
And then increment it.
There you go. Once you've copied it, what do you need to do? Increment it to set yourself up for the next J. All right? We won't visualize this because it'll work. But I will grab this test case here, bring it over here, and I'll get rid of everything here in main. Right, there we go. Oh wait, actually no, not everything in main. No, I do want it. Okay, I don't have anything there. All right, there. Let's print it out. For int I equals 0, I is less than something, I plus plus. I will print out, printf, %d and the line, or no, let's go with filtered of %d is equal to %d and the line. I, and then filtered of I. There we go. So question mark there. How big is that filtered array? Well, we know from the visualization that it was 4, right? Is it always going to be 4? Nope. In fact, I can guarantee you, if I add one more here, it ain't gonna be 4. So how do I know how big it is?
And,
What?
and,
Well, the n is the original array. How big is the filtered array? Now here it would be 5, right? The number of evens, odds in this.
we did have J, but did we, that was just in the function, right?
Yeah, it's just in the function, num odds. That's the size. Yeah.
So, I mean, if you were to like blindly run it and just infinite loop and just ran it until it crashed, wouldn't it still print out all the values before crashing?
Yeah. I'll go ahead and go with 100.
Technically.
What are you complaining about? I didn't use MemCPY, did I? Okay, fine. I did. I already copied it to the notes, so I'm going to get rid of it. I'm going to clean all of this up. There we go. If you just keep driving, won't you eventually stop by driving over the cliff sometime, right? I want to stop. Instead of hitting the brakes, let's just go ahead and keep driving until we run into something, right?
Grand Canyon's over that way.
Exactly. 5, 7, 3, 9, 11. Garbage, 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 garbage. And then eventually, I'm sure that if you went 1,000,000 or something like that, then you'd fall off the cliff or crash, right? Let's go ahead and go with
Do the size of
1,
the
2, 3. There we go. Yeah, can you do the size of? It's dynamically allocated. There we go. So apparently the cliff was 33,623 feet away. And that's where you stopped successfully. That's why you always have to be careful with engineers, because if it conforms to the specifications, you didn't say that it had to survive. We got you to the moon. We didn't say that you'd be alive when you got there, right? All right, so how do I find out that size?
It's not, can you do,
I could do something like this, right? We've got this piece of code here, right? I could cut, paste, right? And then the mods.
why would you want to do that again?
Yeah. Well, the function already did it for me.
Unless you wanted to attach it to a pointer somewhere
Ah.
else or something.
Yeah, what I'd really like is for a function to return both the array and the size of the result, right? Can you do that? Can a function return 2 things?
Not strictly.
No, that ain't a function. Right? That ain't a function in math. That's not a function in computer science. How do we return more than one thing?
Pointer method.
A pointer, a pass by reference variable, int result size. There we go. All right? There's no const in front of it. Therefore, we can make changes to it. In fact, it implies that I want you to make changes to this. Right? Result size is equal to num odds. That's how big it's going to be. Is that the correct way of setting a value in a pointer?
No.
Nope.
You have to do the, I don't
The
remember the exact thing.
star, right? Star. So when I many years ago when I took calculus, of course they expected us to memorize all derivatives and antiderivatives, right? So so the derivative of sine is cosine. The derivative of sine is, or cosine is negative sine, right? I never remembered which one had the negative, so I just took a Post-it note, wrote it down, threw it into my desk, right, as I was working, and by just seeing it there, I was able to drive that into my head over a semester, right? So if you have a pointer, dereference star. If you have a regular old variable, reference ampersand. Put that on a Post-it and put it right next to your computer, right? And eventually it'll just drill into your head which one is which.
So, just to be sure, the star is if you're going from a pointer to a variable, or
A pointer to regular variable,
is a star,
star, which is a dereference.
and then if you put an ampersand, that means you're going from a variable to.
Regular variable to a pointer will be ampersand reference. Ooh, that's nice. They align, well, I guess that makes sense. They align right up. Right? Okay. That means that I have to change my signature up here. And guess what? I should change my documentation, right? The size of the returned array is communicated to the calling function through the pass by reference variable result size. Right?
So if you have like a null pointer, you're not allowed to like dereference that, like it's.
Nope. Bret Hart is not going to let you do that. Right? All right, now let's go ahead and change this so that we're actually grabbing that. Let's go num odds. Bring this up here. I don't have to initialize it because the function will do that for me. And my question is, am I doing it correctly right there? Where did I write those notes? There we go. I have a regular old variable. I need a pointer. What do I need to do? Ampersand in front of num odds. Right.
So the function takes in the pointer value then?
Yep, it takes in the bucket, right? I've got this variable, this memory address, and this contents, and I'm giving you the memory address so that you can set its contents. You're the function now. You're the filtered even function.
So it takes in a memory address so it can put things.
So I can take num odds and put it into that memory address, just like scanf. Scanf, I want you to read in an integer and put it into this variable x over here. What did we have to do? Slap an ampersand in front of the x so that it knows where to write that variable.
Okay.
Right? And now we're doing our own scanf kind of stuff here.
Okay.
Right? Now this will not fall off the edge of the earth because it is flat, remember? Right? There we go. 5, 7, 3, 9, and 11. And you didn't keep going because the function communicated two things, an array and a result of an array. Right? Now, in all the examples that we did up to this point, we didn't have to do that because if I make a deep copy of an array of size n, I told you it was of size n. Right? I should know that the result is going to be of size n. It's only when the calling function needs to be communicated to how big the result is that do you need to do something like this. Two remaining items. Go back to your question. Who is responsible for this memory that's been allocated? Is it filter evens, and so it should free up the result? Or is it main, and it should free up the filtered? What about here? Zoom out here. So, all right, filter evens. Count up the number of evens. Allocate memory, fill it up with those evens, free it up, and then give it back. Write a paper, throw it in the garbage, and then say, there's your paper. So this function is not responsible for freeing it up. If it freed it up, right, it's gone, right? You called a function, it did the work, and then it threw it away. Why'd you call the function? Right? But main captured that memory, and now it's responsible for freeing it up after it's done using it, printing it out in this case. Right? Again, if it's main, not that big of a deal, but if it's anything else, it is that big of a deal, so just get in the habit of freeing it up. Okay. One last item. What if I wanted a filtered version of, say, I don't know, what if I called filter evens on null, -10, and null? Are any of those correct?
No.
I'm giving you a null array, a non-existent array. I'm giving you a null bucket to fill. I'm giving you an array of size -10. Can you have that?
No.
Nope. By the way, you can have an array of size 0. That does make sense. It's just a raw memory address such that nothing has been allocated, right? But it does not make sense to have a negative value. How can we deal with that here?
Input, just check your inputs.
Check your inputs just like you did all this, like you're doing right now, hopefully, for tomorrow's hack, right? Check all inputs. If the array is null, or if the result size is null, or if n is less than 0, it's negative, right? These are all error conditions. Return an error code of 1. That works when the return value is explicitly an error code of integers. This is not an error code.
Return a pointer to one.
All right, return a pointer. What pointer would indicate failure? That I couldn't do anything.
Null.
Null. Exactly like malloc does. If you're greedy and you ask malloc for 80 quadrillion terabytes of data, it's going to say no. And how is it going to tell you no? It's going to return a null pointer. And then you can check for that null pointer and see, was I too greedy or not, right? Was it successful or not? If I give it bad input and it's the pointer value being returned is a pointer, or the value being returned is a pointer, that's all you can return. What if I returned 1? That's the memory address 1.
Which
That probably doesn't belong to me, right? So null is the only sensible thing that I can return, okay? And because this is notes, and I'm going to copy it over here, when the return value is a pointer, the only sensible return value to indicate an error is null. ... There we go. And now I will make sure that this is in the notes. Exercise. And I think that was all. Everything that we've covered with arrays up to this point has been covered in that one example. Pass by reference, pointers, memory allocation, memory deallocation, referencing pointer, dereferencing pointer, right? Or operator, I should say. All right. Any questions so far? No? Okay. Then what we will do next time is valgrind, right? And GDB. For example, let me go ahead and say, I'm just going to give you a really quick preview here, right? And I will go ahead and make this so that I am passing in null instead. There we go. GCC, run it. Segmentation fault. Something happened, right? What happened? You know what happened because you saw me make the intentional bug. Does that tell you what happened? Core dump, right? So I think some of you have mentioned Java before. If something were to happen like this in Java, how would Java react? Yeah.
There might be a JVM crash reports.
All right.
Might not be. If there's not,
Yeah, this thing called a stack trace appears, right? And maybe if you're in the right ID, it's all in red because it is an error, right? Right? And what is that stack trace? It says an error occurred in your code at this line number. In this function. That function was called by that function, that function was called by that function, that function was called by that function. What is that thing again? The call stack, right? It goes all the way back down the call stack to tell you exactly what sequence of events led to that error so that you can go and start debugging. Do you see that here? No. Yeah.
Sorry, I was thinking you meant if you caused a segmentation fault in Java.
Oh. That's not possible because you don't have access to memory.
Unless you're calling a C function with bad input, in which case the JVM, it might be able to pick up on, give you a crash log.
Oh wow, you've worked in JNI before, like Java native interface.
So.
Oh wow. What did you do?
Originally I just wanted, what is it? I forget what the libraries originally intended to work with in high school, but I'm really hoping Project Panama is released.
Okay.
Because that aims to fix most of the JNI issues. There's also JNA, which is community-made Java native access.
Okay.
Which is less of a pain to work with.
Oh, I've never not heard about any of that stuff. So
Yeah.
for those that don't know, in Java you can basically make direct system calls to, like, say, a C library. In fact, the math library does that. Nobody has rewritten the C library. If you look under the hood, Python calls the C math library. Java calls the C math library, right?
Wow. I was trying to call
Why reinvent the wheel?
I guess.
Say
I
what?
was trying to call one of the Windows libraries originally.
Oh, okay. So some Windows native library. Why write code when you don't have to? Right? And it's called JNI, the Java Native Interface, or something like that, where you can make direct system calls. And so, of course, you could seg fault out, and then that bubbles up all the way to the JVM. I was thinking more simple, though. What happens when you do something like a null pointer exception? You get this nice stack trace. No nice stack trace here. unless we use a tool called GDB. Right? And this I'm just going to show you as a quick demo here. What I did is I added this G flag. Right? That G flag says, I want to prep this source code for debugging. Because I don't want to lose all of my variable names, all of my function names, all of the line numbers, right? If I didn't use this, this G flag here, it would just be a bunch of machine code that would be non-readable. Now what I'm going to do is I'm going to fire up GDB on a.out. And I'm going to give myself way more room here. Right? And I'm going to go ahead and go layout source. There we go. There's no source code yet. I will set a break at main. Right? I know something is going to go wrong here, so I'm going to run my program. Right? There we go. Refresh it. Now, unfortunately, I don't know why. I don't know what I did that one day to have really good fonts, but it's no longer good fonts on the screen over here. But it looks way better up there, but not terrible over here on this one. I don't know what the live stream looks like. Does the live stream look decent? Somewhat decent, right? Anyway, what I can do now is I can start walking through my program. Next, 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 right? I can go walk through step by step and see what's going on. I can say print n, right? It has a value of 9 that was set up on line 20. I could say print array, right? Now, unfortunately, that's going to be, oh, there we go. It can do that because it's a static array, right? And I can print the contents there. I can print, well, what's in array sub 0, right? 0. Right? I can stop the execution of a program and look at variables and find out what's going on. This is GDB, GNU debugger, GNU debugger DB, right? And then I can step into that function and I can, walk through this function. All right, nothing's wrong there, nothing's wrong there. But this is quite a long loop here, right? I know that there's nothing wrong there, so what I'm going to do is I'm going to set another breakpoint at line 52 here. Break at 52 and continue so that I can jump down there. Sometimes you have to refresh because it's TUI. So you've probably heard of GUI, graphical user interface. This isn't a graphical user interface. This is a TUI, a text user interface. Right? Ha ha ha. Right. So next. Or I said continue, right? Yeah, continue. So I continued there. Next. And then it died. Right? I wonder why it died. Now I know what line it died at. In fact, I can do a stack trace full. Back trace full. Oh, no stack. Okay. Because it already died. Weird that it wouldn't let me do that. All right, I'm going to have to review, or maybe this is a different version of GDB. But in any case, you can walk through this just like we did with this visualization tool over here, but it's much more sophisticated, right? You can do a lot more stuff over here. For example, you can go out layout next. What does that look like to you? That's assembly code right there, right? If you ever need to deassemble something and look directly at the assembly code that's being run in a program, layout next. There's the assembly code along with the original C code. Layout next. Layout next. I want the, no, that's the assembly code. The other was the machine code apparently. Layout next. All right, there, now I'm back to the original layout, right? Eventually, you will probably be doing embedded system level stuff and looking at assembly code, writing assembly code, debugging assembly code, if you haven't already, are you?
Yeah.
Oh, you are? Okay. Have you used GDB to do it?
That's the class that Professor Netloff teaches.
Okay. Have you used GDB then?
We haven't really used C to do it yet. We've learned just assembly now, and so everything we've done has been strictly in assembly in that class.
Okay.
We'll get to C a couple in
After midterms, I think.
Yeah.
What assembly do you use?
AVR.
AVR? Not
Pretty much
ARM?
all of those instructions look roughly the same as what we
Okay. Move, exclusive or, move L. I don't know what that L is, but push, right? Et cetera, right? So you can scroll through however many lines of assembly there are here. So you haven't used GDB with your assembly code yet?
The IDE we're using, made by AVR, or made by Atmel, has a debugger in it.
Oh, okay.
Maybe based on GDB, I have no idea.
All right, yeah,
The,
probably because why rewrite when you can just use it?
So this would be compiled for x86, right?
Yeah, well, Ubuntu, yeah, I
I
think,
mean, because
Wait.
this is on just on one of Microsoft's servers somewhere.
name, I mean, it's a uname. It's an Ubuntu virtual server. I think, no, this is AWS probably, not Microsoft. Oh, no, you're right, because it is Visual Studio, so who knows? I'm not footing the bill.
It tried to open, I had to use the online stuff because I needed CMake for this hack.
Okay,
It tried to open this in the app Visual Studio.
Uh-huh.
the code.
Oh,
Yeah.
Apple Studio is directly based off of Visual Studio.
yeah, this is
It
a
only runs
Microsoft
on
product.
Windows, I can't get it for Mac.
I know, it's
Huh.
weird. It's just modded Visual Studio, like you reskinned it, added more tools.
Okay. All right, well, I'll go ahead and demonstrate the full usage of GDB next time. Right? Otherwise, I do have a video on it, and to my surprise, it is my #1 video of all time. I think that there are like 200,000 or 300,000 views of it or something like that. I don't monetize my videos, but I did look into it, and with that many views, I would earn a whole $10. Yeah.